Okay, in this video I'm going to talk about certain sums of binomial coefficients. In the previous video I proved that this sum of the binomial coefficients nk for k from 0 to n, so this sum is equal to 2 to the power n. So in this video I'm going to calculate sums of the form so the sum of k multiplied by the binomial coefficient nk for k from 0 to n, and also I'm going to calculate this, and also sum of k squared k from 0 to n, and k cubed, and so on. So I will show how to calculate the sum for any arbitrary any arbitrary power. So let's write here, and so on. And so the sum k to the power s and k from 0 to n for a given s. So I will not give an explicit formula, but I will show how to calculate it. Okay, so basically, recall how we calculated this sum, right? So we calculated it using the expansion of the the formula for how to expand the sum x plus y to the power n, that it is equal to the sum of binomial coefficient k to the power k from 0 to n of binomial coefficient multiplied by x to the power k, y to the power n minus k, right? And so then in this formula we simply set x equal to 1 and y equal to 1. So when we set this, we basically get this formula. So now notice that to obtain this formula, we cannot set any other values. It's easy to see that if we set any x and y to any other fixed values, we will never get this formula. So it's not straightforward, straightforwardly analogous to the proof of this original formula. So what we do, but we still will use this expansion. So basically what we do is we will calculate the derivative of this expansion formula by x. So basically we take a derivative by x of both the left hand side and the right hand side, right? So we do so let's put it this way. So here we do the derivative by x. So the derivative on the left hand side, so it's by the chain rule. So first we take the derivative of the power, so n multiplied by x plus y to the power n minus 1 multiplied by the derivative of the inside, so x plus y by x. So let's write it here. So derivative of x plus y by x, but this basically is equal to 1, right? So, and on the right hand side, yeah, so and on the right hand side what we have is so we have the sum yeah, so I have the sum binomial coefficient, and here we have the, so here we have the derivative of by x, so it's k x to the power k minus 1, and y remains as is because like y it does not depend on x, right? So y is a constant in this formula. So yeah, so basically that's what we get. So now we simply so let's let's write it separately, or like I guess just let's just remove this factor because it's equal to 1. Then we have the formula that we need. I'm not going to rewrite it again. So now in this formula, in the derivative, we set x equal to 1 and y equal to 1, right? So that's where we get, so n multiplied by 1 plus 1 to the power n minus 1 is equal to sum for k from 0 to n k so k and then simply 1 1, so 1 okay, let's write 1 to the power k minus 1, 1 to the power n minus k, but 1 in any raised to any power would be still 1, so we can simplify this basically n multiplied by 2 to the power n minus 1 is equal to the sum for k from 0 to n, basically k the binomial coefficient nk. So yeah, and so basically this is exactly the formula that we need. So this sum on the right hand side is exactly the sum that we need to calculate here, right? So basically we calculated the sum. So the answer is n multiplied by 2 to the power n minus 1. Okay, so yeah, so we can write it here. So n multiplied by 2 to the power n minus 1. So now how to calculate this sum where we have k squared instead of k? So basically we do similar thing here. So instead of differentiating it once, we differentiate the expansion formula. This formula we differentiate it twice by x. So so I'm going to write it here. So here, and we do the second derivative by x. Okay, so let's continue. So we take the second derivative of this expansion formula. So basically we already have the first derivative here. We simply differentiate once more. So on the left hand side we will get n multiplied by n minus 1 x plus y to the power n minus 2, right? And on the right hand side we get n, the binomial coefficient under the sum, and here we have k multiplied by k minus 1 x to the power k minus 2 y n minus k to the power n minus k, right? So this is the second derivative of x, and everything else is a constant. So so now we set so in this formula we set x equal to 1 and y equal to 1. So then we get on the left hand side we get n multiplied by n minus 1 multiplied by 2 to the power n minus 2 is equal to the sum binomial coefficient for k from 0 to n, and here we have basically k by k minus 1 and basically 1 and 1. So because x, so 1 to the power k minus 2 is 1 and 1 to the power n minus k is also 1. So basically we can just remove this. So that's what we get. So now we can expand this. So this is equal to k squared minus k, right? And so then the whole sum, the whole right hand side is equal to like basically two sums, k squared multiplied by the binomial coefficient. So this is like this for k from 0 to n plus not plus but minus k by the binomial coefficient from n to k. Right, so so now we observe that, so this is the sum that we need to calculate, and this is the sum that we already calculated in the previous step, right? So like here when we took the first derivative. So this we can simply replace with n multiplied by 2 to the power. So this sum is simply equal to n multiplied by 2 to the power n minus 1. And then we can express the sum that we need to find for k from 0 to n of k squared n k. It's expressed as the left hand side, so n minus 1 2 to the power n minus 2 plus this plus n multiplied by 2 to the power n minus 1. So and here it can be simplified. So we n is the common factor, and 2 to the power n minus 2 is the common factor, and here n to the power n minus 1 it's simply n to the power n minus 2 multiplied by 2. So if we move this common factor here, n minus 2, then here we get n minus 1 plus plus 2, right? So this is equal to n plus 1, so n minus 1 plus 2 is simply n plus 1 multiplied by 2 to the power n minus 2, and this is the answer. So this is the answer. So this is this sum, also this sum that we needed to calculate, this sum. Right, so and so it's similarly we can calculate basically for arbitrary power k to the power s. Like I don't have the explicit formula, like I don't know if we can like if it's a simple formula, if we can simply deduce it, but it's a recurrent relationship at least. So like it's easy to see that if we differentiate like s times, then here we would get, so on the left hand side we would get something like this. So some n multiplied by some other factors, x plus y to the power some n minus s. And on the right hand side we will get, so here we would get some factors of k, and then this. So basically, yeah, so let's write this actually. So we will get n multiplied by n minus 1 multiplied by n minus s plus 1, right? X plus y to the power n minus s, and on the right hand side we will get the sum for k from 0 to n, and k here, k minus 1, and so on, k minus s plus 1, x to the power k minus s, y n minus k to the power n minus k. So that's what we get. And now basically when we expand this expression, so it will be so this expression, it will be k to the power s plus certain, plus like some like with some coefficients we will get like alpha 1 or alpha, let's say s minus 1, k to the power s minus 1, plus and so on, plus alpha 1k plus alpha 0. So like this alpha, like they can be explicitly calculated when we expand this expression. Like I'm not, like I don't know the exact formula, like it's that's not the point, but basically here in this expression, so everything, so the first term, so this could be like, we could write it alpha s, but it's equal to 1. Alpha s is equal to 1. It's clear that, and the first term is k to the power s. So basically we keep this the sum for this factor separately, and everything else, yeah, so then of course we set x is equal to 1, y is equal to 1, and in the resulting sum, so x and y they cancel, they disappear because it's 1, and so in the resulting sum, so this the sum for k to the power s, this is the sum that we would need to calculate. So k to the power s multiplied by the binomial coefficient, and all previous sums are already calculated on the previous steps. So k to the power s minus 1 is already calculated, and so on. So basically this way we can express the sum k to the power s, this binomial coefficient, we can express it in terms of the previous sums. So it would be like a function, like a certain function of all the previous sums, k to the power s minus 1 and k, and so on, and all lower sums, like the sums with the lower power for k. So so this is a sort of recurrent relationship. So this way we can calculate all of them in terms. So to demonstrate it, let's calculate it for s equal to 3. So for 1 and 2 we already calculated, right? So let's calculate it for the cube, k cubed, right? So we would get here, so n multiplied by n minus 1 multiplied by n minus 2 x, well, when we already set x and y to 1, so we would get here 2 to the power n minus 3, right? And here we would get, so we get, so let's say, so k multiplied by k minus 1 multiplied by k minus 2. When we expand this expression, what is it? It's k squared minus k minus 2. It's k cubed minus k squared minus 2k squared plus 2k, right? So it's k cubed minus 3k squared plus 2k. So this is the coefficients alpha. So it's minus 3 and 2, right? So now we get, so when we expand this, so it would be the sum of, so like I will skip the indices in the sum because they're always the same. So n k cubed minus, so minus 3k squared, so minus 3 sum, so let's write here the k cubed before the, just for convenience, k cubed and k, minus 3k squared and k plus 2k plus 2 sum k and k, right? So now this sum, so this sum we already calculated, it's equal to this, so n multiplied by n plus 1, so n plus 1, 2 to the power n minus 2, and this sum is also calculated, it's equal to n 2 to the power n minus 1, right? So now we express this sum, what we need, so we express it, so the sum k cubed and k as this expression on the left hand side, so it's n multiplied by n minus 1 n minus 2 plus 3 multiplied by this 3n n plus 1 2 to the power n minus 2 minus 2 n, this expression 2 to the power n minus 1, and this is the answer. So like maybe we can simplify it further, like yeah, here I forget 2 to the power n minus 3, of course. So n 2 to the power n minus 3 multiplied by n minus 1 n minus 2 plus 3 3n not 3n plus 1 multiplied by 2, so we can write it 6 here instead of this, 6 minus So here is n minus 3 minus 8, yeah, and minus 3, here's n squared minus 3n plus 2 plus 6n plus 6 minus 8, and this is equal to n squared minus plus 3n and plus 2 plus 6 minus 8. It seems that they cancel each other, like, unless I made a mistake somewhere, but like it seems that this is what we get. And so this is equal to n squared n plus 3, 2 to the power n minus 3. So this is the answer. Yeah, for this sum with n cubed. And so similar way we can calculate for k to the power 4 and so on. So yeah, so this is the method. I don't know the general formula and if it even exists, but this is the way to calculate it like iteratively using a recurrent relation. So like, but here, like this method, like we can see that we used the derivative, which in the original problem setting, like there was no indication that the derivative would be useful. So like it's just we need to calculate these sums, like it's sum of certain binomial coefficient. There is no indication of any kind of derivative anywhere in this problem. So, and it's kind of surprisingly that a derivative, the concept of derivative can be useful in this for this problem. Yeah, so that's it for this video.